morning, everybody. Yeah, I'm happy to be here and that we are able to organize this. I would like to complement a little bit the story of Frederic, because we're now moving a little bit higher. I'm going to talk a little bit more about UAV as a platform for phenotyping, and I will show you some examples that we have done over the past years. It's more providing an overview, and especially you see a lot of people here on the first screen. They are all involved, and when you have questions, please address them to me after the speech or later on, so I can also pinpoint you to the right people. So if you look at a typical plant breeding field, then it seems that UAVs are almost completely made for it. Here you see a field with maize trials with 3,000 plots. And you could say that when you look at UAV platforms, they are a very nice platform to get a complete overview of such a large field quite quick. You can apply different kind of sensors on the UAV. And compared to satellite-based platforms, you also have this increased spatial detail, which is really required for plant breeding type of applications. But we also face some challenges. If you look at the remote sensing domain, then we're using the remote sensing processing chain to get from the acquisition of the data to the final traits as a product or a variable, which is required for understanding the plant systems that we're looking at. But during this processing, several things have to be taken into account. We need to take into account the potential errors due to changes in geometry, especially if we want to monitor the crop over time. We have to take care of elimination effects. There are all kinds of ways how you can analyze the data. And in the end, what you also see increasingly is that and there's a changing interest from the plant scientists to go from really the plot measurements to the individual plants, and that's quite challenging. So it's important that we work together as two domains to get this complete processing chain covered. And for the UAV type of application, there are even more questions. Which UAV platform to use, what kind of camera, what kind of flight planning, all these kind of issues that you need to take into account. And what we are looking at is that we want to start from what actually needs to be monitored, and in a sort of backward engineering approach, look back on what kind of requirements are then required for the UAV platform, the camera systems, and for the whole processing chain. So this is important to understand together as experts from different domains in order to get to good quality solutions. Now, within our group, since 2012, we have established the Unmanned Aerial Remote Sensing Facility, where different groups are working together using UAVs as a platform to monitor and map ecosystems for all kinds of applications. So you see here habitat mapping, forest structure and forest monitoring, agricultural systems analysis and precision agriculture, and also phenotyping. That's in fact a little bit since 3 or 4 years. So we have a whole range of facilities. We have different types of drone systems. We have a whole range of camera types, and we also organize the whole regulation so that the pilots can do their activities in a safe way. So what I would like to present to you today is a little bit the type of sensor systems that we're using. And when we started, we wanted to continue with our hyperspectral remote sensing knowledge that we had from more the manned airborne systems. And we wanted to do that on a UAV platform. And at that time, in 2012, there were only a limited number of hyperspectral mapping systems available. So in that sense, we thought, okay, why don't we develop our own system? So we developed the HIMSI system. But we also got across some problems, because it was a push broom system where getting geometrically good quality image data was still quite challenging. So already A few years later, we bought an on-the-shelf system, the Ricola camera, which is a frame-based camera, also hyperspectral, but in that sense got a little bit better geometrical results. And for phenotyping, that was more better. Also, when you want to move into applications related to disease assessment, for example. Now, what I also want to present in this overview is some work that we were able to do with our Lidar UAV system, which we were able to establish in 2018. So we have now 3 years of experience with that. And we also applied it already in several phenotyping projects. Now, next to that, we have some experience now with sun-induced fluorescence. And we also are using the regular multispectral type of camera systems. Now, moving to the hyperspectral system that we already have in place now for 8 years, HIMSI. When we developed this system, we ran a little bit into the problem that this geometry is a challenging problem. So you have scan lines that we acquire with a push-broom spectrometer, and in order to get a good quality complete image, we need information to align those scan lines. So our postdoc at that time, Juha Sulemainen, he came up with a solution that you could use RGB type of images, so the orthomosaic that is derived from an RGB image, and you can use that to get a good quality alignment of the hyperspectral lines. So in that sense, we got to a complete solution where we were able to acquire in one go information on the RGB, so a complete RGB orthomosaic with quite often a detailed resolution, depending a little bit on the flying height. We were from the combination of the photos in the orthomosaic and applying the structure photogrammetry method, we were able to derive a digital surface model, so information on the height of the surface and also the height of the crop canopy. And as final result, also the hyperspectral data, so the spectral data, in this case in a range from 450 till 950 nanometer. And here you see some spectra that were acquired over an operational field where we compared the spectral measurements from the HIMSI system with the reference spectra that we acquired in the field. And you see that they have a good resemblance. So with that camera system, we have done several experiments over the past years. And we started with some experiments in cooperation with other researchers within Wageningen. So one researcher, that is Gerlinde de Dijn, she's interested in the effects of the winter cover crops on the follow-up summer crops to see what kind of positive or negative effects those winter cover crops have. And she had established this trial over here with the dark green oat crop and the light green endive crop. And what she was interested in is the question, we are doing regular field measurements, which is quite a lot of work. Can we now replace those field measurements with measurements from UAV-based hyperspectral measurements in this case, in order to characterize the field traits, the crop traits, initially at one point in time, but over a longer term, also over time to follow the crop development. So what we did is that we acquired hyperspectral data over the field. It was a little bit later in the season. We also acquired data of the crop, in this case, chlorophyll, nitrogen, the plant height, and also the biomass. And we used, in this case, a simple machine learning model, partially squares regression, to establish a relation between the plant traits and the spectral data that we acquired with the hyperspectral mapping system. In this case, we were interested to which extent we could characterize these traits at the plot level. So initially, we established the model at plot level, but when we had established the PLS model, we could also apply it to all pixels in the image And in this way, we were able to map, in this case, for example, what you see here, the oat chlorophyll concentration within the plots. So this kind of result does give the researchers also not only one observation per plot, but also the variation of, in this case, chlorophyll within the plot. So what we were interested is to evaluate the effect of the treatments, the winter crop treatments, which show up in the field measured traits. Can we also reproduce them with the UAV measured observations? And here you see the results. You see here on the x-axis the treatments, and what you see, for example, for the height is that based on the height from the digital service model that we acquired with the HEMSI system, we were quite well capable to reproduce the field measured height. For biomass and nitrogen, this on some treatments, this was not completely well possible, and the overall differences we were able to capture, but on some higher concentrations it was more difficult. But for leaf chlorophyll, we got a very good reproduction from the UAV observed traits with the field measured traits. So we are now continuing this research already for a few years. I will not present it here, but we have been able to follow the crop also over the growing season and are able to provide this information to the studies of Gerlinde de Dijn. So the next example on the use of hyperspectral remote sensing that I would like to show you here is an example on mixed cropping systems, which is something that is quite a lot of research ongoing in the Netherlands, but also especially in Wageningen, on how mixed cropping could benefit crop growth, especially in organic farming systems. And the group of Dirk van Apeldoorn is doing quite a lot of work over there. And we also followed for 2 years with the hyperspectral mapping system, the different crops in this mixed cropping system. In this result, I would like to focus on potato, where there was a comparison made on a treatment where one type of variety was used compared to 3 varieties in a mixed cropping system to reduce the pressure of late blight. So what you see over here are the RGB images that we acquired over the growing season. So you see here on the development of the crop over the growing season for different plots. And you see a clear difference in the effect of late blight in the parts where there is the mixed varieties compared to the one variety. And what we did is that we acquired also hyperspectral data over these plots. And the first step that we wanted to make is to check to which extent we were able to reproduce the plant traits of this potato crop over the growing season. And in this case, we used a simple vegetation index-based approach. So we used different types of indices for different types of plant traits. And you see over here that we got quite a good result with an R squared of 0.65 and a root mean square error of 6 for leaf chlorophyll. And you see that also for the other traits we were doing pretty well. So these results are published in a paper by Marcin Franceschini. We also compare that to ground-based observations we made with the crop scan instrument to check to which extent the spectra that were acquired on the ground could be reproduced with UAV-based spectra. And you see that for some of the traits that works pretty well, and so there's a good relation between the spectral observations on the ground and from the UAV. But you see that especially with the spectral observations which are required for leaf chlorophyll observations, that is much more difficult, and you get a different relation that you need to assess there. Now, partly this is also caused by the effects of the geometry. You see here 2 plots that were acquired. And you see that on the right plot, the geometry is well reproduced. But on the left, you also see that in this line scanning principle, there's quite a lot of disturbance due to the movement of the UAV platform, which is difficult to correct for this kind of line scanning cameras. Okay, what we also wanted to do is make a next step is to use the hyperspectral data to characterize late blight levels in a potato, also in the same experiments. And in this case, we moved from the line scanning camera to the Ricola frame camera. And what you see here in the upper part is the observations that we made close range. So from a distance of 2 meters over the potato canopy, and you clearly see the late blight effects on the leaf, but also represented in one of the images over here in the hyperspectral data. What you see on the lower part is that we compared here the close range Ricola observations with the UAV-based Ricola observations to characterize the late blight infestation. And you see that with the close range observations, we clearly can distinguish the late blight on the leaves. But with the UAV-based observations, you still see some effects. For example, when there is a high late blight infestation, but when this late blight infestation is pretty low, then it's more difficult to identify. And that both has to do with the pixel size, because we are here looking at pixels of 2 centimeters, but also with the point that especially the late blight is coming from the lower part of the canopy up, and especially in the earlier states of late blight infestation, it's difficult to distinguish. Okay, so here we have looked at the opportunities of using hyperspectral data. I now would like to move a little bit to the opportunities of using UAV-based platforms to characterize the structure of the plant canopies. And the first example that I would like to show you is an example where we use the RGB observations to characterize the maize height in a very large-scale experiment, which was laid out by Lammert. What we did is we applied structure for motion on the imagery that we acquired over the growing season. So we were able to establish the digital service model from the maize plots. And we had a ground model that we established early in the season. And from that, we could establish the crop height. In this case, we were using ground control points to get a good geometry and a good geolocation of the crop height model. And when we compared the crop height model with the manual observations, which were made by the Lammert people, we saw that initially there was quite a large bias and there was a good reproduction of the height, but with a bias. And what we saw is that in fact that has very much to do with how you represent the height within the plot. And so there's quite some variation in the plot. So do you take the maximum height, or do you take a certain percentile? And for example, when we take the 99 percentile, like over here, then you already reduce quite a lot of the bias. So this is quite an important point. Do you look at the plot level of the observations, or can you look also at individual plants? Now over here you see the product that we derived for the complete 3300 plots, and it shows that we were really capable to distinguish between different the height between different plots, and it is a good starting point for moving towards UAV characterization of height of maize over the growing season. But we also saw some limitations, and also there's an interest of the plant breeders on getting not only height but also other characteristics of the maize canopy within the plot. So there we introduced a LiDAR-based UAV system. In this case, we were able to acquire the Rycopter system of Regal, which is a very high advanced LiDAR system Over here you see the characteristics of the LiDAR, where in different kinds of characterizations of the LiDAR system, we either can fly with low density flights, which will allow for somewhat longer flights with a point density of 400 points per square meter, but we can also increase the point density by flying at a lower speed and at a lower height. And then you see that you can get quite detailed representations of plant canopies, where you get not only information on the top of the canopy, but also in detail on the inner plant structure.
Yes, Lammert, 5 minutes left.
Yeah, thanks. So what we did is that we applied this system to different experiments. So initially, this is a maize plant breeding trial with also 1,000 plots, where we derived the plant height from LiDAR. You clearly see the differentiation between the plots, and also you see that certain plots have a much higher height compared to other ones. But we were also interested in more other characteristics of the maize, and that is currently something that we're working on. If you look at this example over here, a transect over the maize, then you clearly see that you can distinguish individual maize plants. And if you look at the history of individual maize plants, you can clearly see that you can also distinguish the number of points on certain heights, which can give an indication on the distribution of biomass within the maize plants. And this is currently something that we're working on to develop further. So finally, what I would like to show is an example where we applied in 2019 the LiDAR UAV on an experiment to characterize biomass and crop height for different crops in an arable farming system. So what we did is that we acquired UAV LiDAR data over the growing season at 3 points over time. We also acquired validation data in the field, and we applied a crop height estimation method, and also a biomass estimation method, the 3DPI method, which is looking at the distribution of the points in the point cloud over the different heights of the crop in the field. And we were able to check the quality of the crop height estimation and the biomass estimation. Over here you see the crop height estimation for 3 different crops: potato, sugar beet, and winter wheat. And you see that for all these 3 crops, it works quite well. And you see that in general, it is quite close to the 1-to-1 line, but also over the growing season, we get a good result. For the biomass, we got a more differentiated result, where for sugar beet and winter wheat, we got quite a good reproduction of the biomass. For potato, there was it was much more difficult, and it also has to do with the characteristic of the crop in relation to the 3DPI method. Potato has quite a close canopy, where also the LiDAR points of the LiDAR UAV will not penetrate, and as a result, you will not have much points within the canopy, as you can see over here. Now, based on the models that we established, we were able to produce height maps and also biomass maps, which we can use as output and which can be analyzed by the crop scientists. Okay, so to finish off, UAV-based phenotyping is increasingly accessible and affordable. It's complementary to ground vehicle field observations, because for the development of the models, field observations are crucial. The automated processing is critical and also needs attention, especially the geometry. We have ground control points, so with RTK that is increasingly possible, but still it is very challenging, especially when you want to go from observations from the plot to the plant level. We are looking currently into the use of object-based approaches to identify plant segments, and characterize the properties of those plant segments. Our colleague Benjamin Brede is looking into advanced trait retrieval methods also for UAV-based LiDAR using ray tracing approaches. And we're looking into the opportunity to use multimodal approaches where we combine hyperspectral and point cloud-based observations for disease assessment. Okay, so this was my presentation. When you have questions, don't hesitate to contact me. And I hope there's still some time for questions, but let's see.